Hello, everyone. My name is Haiying Sun. I am a postdoctoral fellow from the Hong Kong Polytechnic University. Today, I am glad to give you a presentation entitled Study on the Impact of Relative Position on Wind Turbine on Power Output Performance. This presentation contains 4 sections. Let's go right into the first section. I am going to talk about the weak effect problem in wind farms. Actually, all operating wind turbines generate wicks behind themselves. Specific phenomena include the deficit of momentum and the increase of turbulence intensity. When wind turbines are installed close to each other, the effect of weak interference becomes serious, leading to the power reduction of wind farm. To estimate the weak effect quickly, some simplified weak models have been developed. Here demonstrate several commonly used weak models. These models are pretty simple, but they all have limitations, and they cannot simulate three-dimensional distribution of wind speed. To investigate the influence of relative positions of wind turbines on power output performance, a more advanced weak model is necessary. Therefore, this study first develops a 3D weak model and then investigates the impact based on this weak model. In the second section, a novel 3D weak model developed by our research group will be introduced. Most wind farms cannot produce as much power as they were predicted, caused by inaccurate weak model and inefficient wind farm prediction tools. The linear weak model assumes the wind distribution at any downstream distance is the same. Based on the linear weak model, 2D weak model was developed, which can estimate the Gaussian shift wind speed in the horizontal direction. However, these weak models cannot consider the wind variation in the vertical direction. Continuing the aforementioned study, a novel analytical 3D weak model has been presented to help describe the wind distribution in space at a wind farm. The weak model is based on the momentum conservation theory and assumes that the wind deficit is Gaussian shift, and the wind velocity is continuous at the weak boundary. It can calculate the wind velocity at any spatial position with high accuracy and little computational cost. The weak model considers the head direction's influence, which makes it more advanced than other analytical weak models. The expression of the weak model is demonstrated. There are 3 assumptions in the weak model. The first assumption is that the wind velocity deficit at downstream distance is Gaussian distributed. The second assumption is based on the momentum conservation theory, and it means that the flow flux is conservative in a specific area at any weak section. The last assumption is that the wind velocity is continuous at the weak boundary. In the next section, I will introduce the impact of downstream distance, horizontal distance, and hub height wind turbines. In the following part, the 2 adjacent wind turbines will be taken as an example to investigate the impact of hub height change of one wind turbine on another wind turbine. Changing the downstream distance between 2 wind turbines has no influence on the upstream wind turbine, but may improve the power performance of the downwind one. Due to the weak effect, the equivalent wind speed of the downstream turbine is much smaller than that of the upstream one. At the original hub height, the equivalent wind speed increases from 385 meter downstream position to 1,540 meter downstream position. If increasing the hub height, the equivalent wind speed will also increase significantly. The effect of downstream distance on power is similar to that on equivalent wind speed. At a certain hub height, the increase in the downstream distance can increase the power to a certain extent. However, when the wind speed is larger than rated wind speed, the power performance will not continue to improve. With a higher hub height, the downwind turbine can reach the rated power at a relatively close downstream position. Changing the horizontal distance is another way to improve the performance of the downstream wind turbine. It is clear that increasing the horizontal distance will lead to an increase in equivalent wind speed, as the effect from the upstream wind turbine can be avoided. For a higher hub height, the turbine can have a larger equivalent wind speed at the same horizontal distance position. When the hub height increases to 40 meters, it only needs to move 40 meters horizontally to avoid the influence of the wick effect. For the power output, as the lower hub heights, increasing the horizontal distance can significantly increase the power output. For example, at the original hub height, the power at the central position is only 500 kilowatt. As the horizontal distance increases to 55 meters, it quickly increases to rated power of about 1,500 kilowatt. Well, when the hub height is larger than 40 meters, which may be different in other cases, the power output performance will not continue to improve. Changing the hub heights of either the upstream or downstream wind turbines may help improve the power generation. Changing the upwind turbine will have a significant impact on both itself and the downstream wind turbine. The downwind turbine has the smallest equivalent wind speed when it is fixed at the same height as the upstream one. The wind deficit is maximum at the hub height. Therefore, no matter increasing or decreasing the upstream wind hub height, the wick impact on the downstream will be reduced. This phenomenon is especially noticeable when the two turbines are close together. The impact on the power of the downstream turbine is even more pronounced. At 5D downstream position, the power could be improved from 450 kilowatt to 1,330 kilowatts. While at the 10D downstream position, the power output can be improved from 830 kilowatt to 1,400 kilowatts. One thing to note is that moving the wind turbine at a certain height may cause different impacts on the power output. Changing the hub height of the downstream wind turbine has complicated influence on the downstream turbine itself. When increasing hub height, the equivalent wind speeds and the power outputs at all downstream positions increase significantly. When decreasing the hub height, the equivalent wind speed doesn't change monotonically with the hub height. At the 10D downwind position, the equivalent wind speed decreases with hub height, while at the position before it, there is a curvilinear relationship between the hub height increment and the equivalent wind speed. At the 5D downstream position, this phenomenon is most significant. Increasing the upstream hub height will decrease the weak impact on the downstream turbine, which will increase the equivalent wind speeds of both upstream and downstream turbines. Increasing the downstream hub height can increase the equivalent wind speed of the downwind turbine. Decreasing the upstream hub height will reduce the equivalent wind speed at the upwind turbine. But this may also reduce the wind's impact on the downwind turbine and increase the equivalent wind speed. Specific influence depends on the relative distance between two turbines. In the next section, the main conclusions drawn from this study are summarized. Firstly, an engineering three-dimensional weak model is introduced. The weak model has high accuracy and can quickly predict wind speed at any downstream position and at any height. Secondly, the hub height and the layout have a significant impact on the wind speed and power performance of its own and its downwind wind turbines. For two wind turbines, increasing the relative distance in downwind direction and horizontal direction can both avoid the weak impact on the downstream wind turbine, thus increasing the wind speed and power output. Special attention should be paid when changing the hub heights of wind turbines. Increasing the hub height is definitely beneficial to power output, but decreasing the hub height may have different results. The influence from leaks can be reduced, but the equivalent wind speed will be decreased as well. Finally, overall, the influence should be evaluated according to the specific hub height increasement and relative downstream distance. That's all about my presentation. Thanks for your attendance.